The James Webb Space Telescope can see galaxies 13 billion light-years away. So why can't it easily look at Mars? That sounds backwards. Closer should be easier. Brighter should be clearer. But for JWST, the closest objects in space are actually the hardest to see.
JWST was built to catch whispers from the early universe. Yet its biggest challenge might be the blinding glare next door. Why is looking at Mars harder than peering 13.5 billion light-years away? And how do you turn a deep-time telescope into a fast-tracking, glare-taming planet hunter? Keep watching as we break down the proximity paradox and show how instrument tweaks and exposure tricks let JWST read hidden layers in nearby atmospheres and chase potential water plumes on icy moons.
NASA's James Webb Space Telescope captured new images of planet Jupiter. Take a look. NASA released these photos. The Great Red Spot, a famous storm so big it could swallow Earth, is also visible, appearing white in the image. Infrared camera. In one image, you can see a close-up of the planet and the auroras at its northern and southern poles.
If JWST can hear a galaxy whisper from the dawn of time, why does Mars make it squint? JWST was tuned for faintness from the start. Its gold-coated primary mirror works at cryogenic temperatures, so the telescope doesn't glow in infrared and drown out the signal. The detectors sit cold too, with ultra-low noise, so a trickle of photons stands out from the background. Long exposures stack up those photons from dim, distant targets until a clear spectrum appears. That works beautifully on redshifted galaxies that trickle light to us. The whole system, optics, detectors, and observing modes, leans toward patience and sensitivity rather than brute brightness.
Biggest planet like you've never seen it before. This composite image of Jupiter captured by the James Webb Telescope in July.
NASA says the images will give scientists more clues to discovering what Jupiter's inner life is like.
Well, we're getting some.
A wide field picture shows Jupiter's rings as well as two of its moons, and scientists say the fuzzy spots in the lower background are likely gas.
Now, shift to our neighborhood. Planets nearby are infrared lanterns. Their sun-warmed clouds, hazes, and surfaces radiate strongly, and they move against the stars fast enough to matter. Brightness hits one problem, saturation. Motion hits another, smear. If you overfill a pixel well, the detector response goes nonlinear and leaves ghost signals that linger, known as persistence. If the target slides during an exposure, fine features blur out. The same sensitivity that reveals a galaxy's feeble glow can become a liability when a bright disk floods the sensor in seconds. Think about flux. Some galaxy programs chase nanojansky-level sources, tiny energy trickles per unit frequency. Jupiter's infrared output, at many wavelengths, is orders of magnitude higher per pixel on JWST's detectors. The dynamic range has a ceiling. Once the incoming rate outruns the pixel's capacity before readout, the data stop being trustworthy. You don't just lose brightness information. You lose shape and depth of spectral lines that carry chemistry, temperature, and wind stories. This is where bright object limits enter the planning. Each instrument and filter combination has a threshold beyond which nonlinearity and saturation distort the measurement. Cross those limits and the spectrum flattens, absorption features clip, and the detector can carry a memory of the bright frame into the next one. For atmospheric science, that's painful. You want the exact depth of, say, methane or carbon dioxide bands, not a flattened plateau. Once nonlinearity sets in, even careful calibration can't fully recover the details. Here's a simple way to see it. Set a camera for starlight, and then walk into a stadium at noon. The sensor floods. Short lines smear if you keep the shutter too long. The fix is to cut the light reaching each pixel and cut the time the shutter stays open. JWST follows the same logic with space-grade tools. First, subarrays. Instead of reading the full detector, JWST reads a small region around the target, which speeds up the readout. Faster readouts mean shorter effective exposures before saturation, keeping the signal within the linear response zone. That preserves the depth and shape of spectral lines. It also reduces persistence because pixels do not overfill as easily. The telescope can take many quick snapshots, all within the safe range, and then combine them. Second, neutral density, like strategies. JWST switches to narrow filters that only pass thin slices of wavelength, lowering per pixel brightness. It uses shorter integrations and dispersers, grisms, or prisms, to spread the light across more pixels. Spreading a bright source into a spectrum drops the intensity that lands on any one pixel while keeping the information content. You sacrifice brute flux, but gain clean, unsaturated data where chemistry lives. Dialing back exposure and cropping the detector flips the script. A machine built to listen for the softest echoes becomes a glare-taming imager for our own backyard. With these modes, nearby worlds stop screaming at the sensor and start speaking in calibrated lines and bands. We handled the light. Now we have to keep up with planets that won't sit still. How do you keep a 6.5-meter mirror locked on a target that drifts faster than a cruise ship seen from space? The observatory was born to stare, hours at a time, barely twitching, soaking up faint photons from the distant past. Solar system targets don't wait around. As they sweep across the sky, their apparent motion can reach tens of milliarcseconds per second, enough to smear a disk during a normal exposure.
We hadn't really expected it to be this good, to be honest. It's really remarkable that we can see these details on Jupiter together with its rings
that photobombed the image. Details that wowed even the scientists themselves. Shows auroras at its northern and southern poles, faint rings, its 2 tiny moons, and even other galaxies.
The hardware can point with extreme stability, but stability alone isn't enough when the goal is to track something that won't hold still. You need the pointing to predict where the target will be, not just where it was when the exposure began. If the telescope doesn't track, you feel it immediately. Planetary disks soften. Narrow spectral lines swell and lose contrast. Cloud bands turn into muted streaks, and any tiny hotspot or auroral arc fades into the background. High-resolution spectra depend on razor-thin features, and those features survive only if the source sits still relative to the detector. That forces guiding to work not as a static lock, but as a dance that anticipates the next step. Moving target tracking solves this by separating the roles. Guide stars stay the anchors, but the observatory continuously slews to match the planet's path, so the planet remains fixed on the science detector even while the sky drifts by. The motion isn't jerky. It's smooth, computed ahead of time, and updated as the observation proceeds. The science instrument keeps its pixels trained on the same spot, while the telescope quietly paints the trajectory under the hood. Those trajectories come from ephemeris-driven pointing. Teams feed in high-precision paths from tools like Horizons, which predicts where a body will appear down to tiny fractions of an arcsecond. With that on board, the fine guidance sensor holds a guide star and measures minuscule shifts, while the control system adds a slow, deliberate drift that mirrors the target's motion. The result is a relative freeze frame. The planet stands still on the detector even though it slides across the sky. You see the payoff in real data. Jupiter, observed with NIR-CAM imaging and NIR-SPEC spectroscopy, holds a crisp limb, letting faint auroral curtains at the poles pop against the bright disk.
The Webb images are taken in infrared and artificially colored. Here, the great spot is rendered in white because of the amount of light it reflects. Most images of Jupiter show it in swirls of beige and red, like this animation from the Hubble telescope. Jupiter is the latest cosmic wonder captured by the Webb telescope as it orbits the Sun 1.6 million kilometers from Earth.
High-altitude haze layers show up because the spectral lines retain their native widths, and the instrument can split methane and H3+ emissions without crosstalk from motion blur. On Mars, rapid scans build thermal maps that cleanly separate afternoon warmth from pre-dawn cold. Carbon dioxide absorption bands keep their depth, so retrieved temperatures and column densities don't get washed out by drift.
A wide-field picture shows Jupiter's rings as well as 2 of its moons, and scientists say the fuzzy spots in the lower background are likely gaps.
The Webb images are taken in infrared and artificially colored. Here, the great spot is rendered in white because of the amount of light it reflects.
Bright targets add one more twist. Instead of one long integration, JWST fires off a rapid train of short exposures using fast subarray readouts. Each frame stays within the linear range, and each lands along the tracked motion path. Later, software aligns the stack with sub-pixel accuracy, reinforcing the signal while discarding any frame that shows a spike or an artifact. You get the time resolution to follow changes and the dynamic range to avoid saturation. This is the pivot from statues to sprinters. Precise moving target tracking, fused with rapid read exposures, turns what would be a smeared glow into chemistry-rich maps. The telescope keeps auroras narrow, limb hazes defined, and spectral lines honest, so the physics doesn't get averaged away by motion. With stable, unsaturated data in hand, the next step is straightforward. Start peeling. Layers of clouds, temperature gradients, and trace gases separate cleanly, and features that looked familiar begin to carry new clues about circulation, seasons, and energy sources we thought we had already pinned down. The same sensitivity that teases out faint galaxies now pulls detail from nearby worlds. JWST resolves auroras threading Jupiter's poles, traces methane and CO2 that swing with seasons, and teases hints of plumes where sunlight glares off ice. Those are not distant echoes. They're present-day processes, mapped in infrared with line-by-line precision that holds up under bright targets. Keep an eye on Europa and Enceladus. Teams will ride narrow filters and fast reads to search for weak water and organics flashing through the glare. The paradox holds. The closest targets fight hardest. And that is exactly where the next surprise tends to surface.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.